So in this video, we'll look at the current solution we have for the merge k-linked list question and see if we can improve it. So just to review, the algorithm looks at the front value of all the linked lists, finds the minimum, puts it in the result linked list, removes that value from this copy linked lists, then keeps going until there are no more values to add. So really there are a couple places in this while loop that we need to look at. These two O of k lines can sort of be combined into one by iterating, but that's not really an optimization. Here, this is sort of annoying that we have to look through all the linked lists again to find the one that matches that minimum value. It would be great if we had a mapping from the value of the linked list to that link. So the key idea here is keep a mapping of the value to the linked list. That way we don't need to iterate through the linked list again to find the one that corresponds to the min value. We can think long term that if we optimize this to have a mapping, and then somehow optimize a way to get the minimum value faster than O of k, and then optimize this while condition, we can get to a better solution. So let's start with optimizing this by having a mapping. Let's actually just put this out here. Keep a mapping of the value to the linked list. Well, whenever you think of mapping, you think of dictionary. What is this dictionary going to map? It's going to map val to link. Well, what if linked lists have the same value? This should be val to links. It's going to be a number mapped to a list of linked lists. So instead of using a regular dictionary, we can use a default dict. Just import it right here from collections, import default dict. And the default is going to be a list. Then let's add all the linked lists to this mapping. For link in copy linked lists, val to links, link.val.append link. Let's print val to links just to see what happens here. Let's just return so we don't execute the rest of the code. Okay, we got a default dict of mapping 1 to link 1, 2, 2 to mapping link 2, 4, 3 to mapping link 3, 3. So it seemed to map correctly. I guess in this example, 1, 2, 3 are all unique, so there's no list of linked lists. Okay, so now we have a mapping of the value to linked list. This logic here becomes pretty duplicate. So let's just comment it out. And now we can find the link basically being this variable val to links min val dot pop. So I'm using pop because pop is a constant time, and that will actually pop off one of the linked lists in our mapping. Pointer.next equals link.val. Pointer equals pointer.next. And let's save and see what happens. Let's just remove this to make it really clean. Like this, run it, pop from empty list. Okay, that makes sense in our solution because every time we're popping off from a list, and that could be empty. So what should we do? Well, we know that if we've popped off the last linked list, then there are no more linked lists mapping to that min value. So we can do something like if len of here is none equals 0. Let's just close this like that. Then we should just delete the mapping because there are no more linked lists mapped to that min val. And the issue that this is causing is the next iteration, that min value is going to be the min value, but there's not going to be any linked list mapped to it. And then we actually forgot one part. Every time we're popping off, but nowhere in the code except for up here, are we ever adding a linked list back to this mapping. Well, if link.next exists, then we need to add the mapping of the front of link.next to link.next. Val to links, link.next.val equals link.next. Let's save it. Let's run it. Okay, again, we're popping off an empty list. I assume, well, this line's not even right. It should be append. I don't think that's going to fix it, but let's see. Well, this logic is wrong. This is legacy logic where we loop through the copy linked lists. We're not changing copy linked lists anymore, so I'm assuming that might be causing it. So let's remove this. Let's get min val is actually the min of val to links. Run it. Min arg is an empty sequence. Okay, well that's because this condition is wrong because we're not changing copy linked lists. We're actually not even using copy linked lists. So let's actually just replace this, delete this copy just to really make the code clean. And here should really be if there are any values in val to links. Cool, and it passed. So it's a little hard to read the code. I'm going to remove the terminal output. But basically this is checking, okay, are there still values mapped? And if there are, then do this logic. But if there aren't, then that means we ran out of linked lists to map. Okay, so let's look at the runtime. Let's scroll all the way to the top. Here, this is constant. This is going to be O of k. Appending to a list is constant time, constant, constant. This is actually constant because taking the length of a list is constant. So this line, so how many keys can there possibly be in val to links? Well, the initial loop, there can be max k keys, but you might be thinking, okay, as we're adding and deleting links from that mapping, won't it grow? Well, no, it can't, because if there are no more linked lists mapped to a certain value, it will get removed from the keys. And so basically, scrolling all the way to the top, the mapping would include 1, 2, and 3 as keys. But then when we've looked at all the linked lists mapping to 1, it will get removed from the keys, and then 2 already exists there. So at a certain time, there can only be k unique numbers mapped in val to keys. So this min actually still takes O of k. This pop is still constant, 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 constant. Deleting from a dictionary is constant, constant, and appending is constant. So what is our final runtime? Well, how many times does a while loop run? Well, even though we changed the condition, it still runs k times n times because it has to go through every number in all the linked lists. So the current solution is still k times n times k. So the previous solution in the previous video was k times n times k, and we've still got k times n times k. So you might be thinking, okay, that's a lot of work to do nothing, but notice how we've removed all the O of k runtimes except for one line. So if there was some way to get this minimum in less than O of k time, we've optimized the solution. We don't have to worry about any other place because everything else is constant time. And that's exactly what we're going to do. So we're going to introduce a new data structure called the priority queue. I felt like the priority queue is not a large enough data structure to warrant its own video, but we're going to sneak it into here and optimize this solution. So a priority queue is a data structure that allows you to put items into it and get items based on a priority. So from queue, import priority queue, pq equals priority queue. And then when you do pq.put, the value that you're putting in is going to also be the priority. So pq.put 1, then 2, then 3. 1 has the highest priority, so pq.get is going to return 1, then 2, then 3. For some reason, negative numbers have a higher priority, so pq.put -1, 1, and -5. pq.get will be -5, -1, and 1. You can also put tuples where the first number is the priority. 1, hello. 2, world, pq.get will return a tuple, 1, comma, the string hello, and then 2, world. You can check if it's empty by pq.empty. Priority queues are really useful because they're usually implemented with heaps, which allows you to put and get in log n time, where n is the length of the priority queue. I will link some more documentation down below, but let's use this to speed up our solution. From queue, import priority queue. pq equals priority queue. pq.put link.val. And then now to get the minimum, it's just pq.get. Doesn't even need to be min, it's literally just like that, which now takes log k time, because the priority queue will at any time have max k values. Here we don't need to do anything because the get actually removes it from the priority queue. Here though, we need to put link.next.val into the priority queue. Save it, exit and run it, and it passed. So now let's call this find min val solution, and this will be val to link solution, and now finally priority queue solution. Final runtime will be O of k times n times log k. So we actually optimized from log k times n to log k, and interviewers really like these small optimizations because it shows that you know your data structures, you know how to think about the best solution and think about ways to improve it. So let's review all 4 solutions and think about what concepts we used and what we learned. So the brute force solution, you put all the values of all the linked lists into a list, sorted it, and created a final linked list. And here we took advantage of the sorted built-in function and it got us comfortable with building a linked list. The final resulting runtime was k times n times log k times n. And then we used a solution that took advantage of the fact that the lists were sorted by looking at the front of all the linked lists, found the minimum, put it in the result linked list, removed that value that we've added, kept going until there were no more values to add. We copied the input because we didn't want to mutate the input, and then kept going until there were no more values, found the minimum value, found the linked list that was mapped to the minimum value, and then added that value to the result and then returned it. The final runtime was k times n times k. Then we saw that we could optimize this part by using a map to map the value to the linked lists. So we used a default dict to map val to links, actually saw a way to optimize the while condition so that it's constant time, found the minimum value, found the link that corresponds to it, deleted that min value mapping if there were no more linked lists, and then added a mapping to the next value of that link that we just popped off, and the final runtime was k times n times k. But we did that because we wanted the only line to take O of k time to be this min call, and then use a priority queue to decrease that runtime from O of k to log k, so that the final priority queue solution is k times n times log k. This concludes the 3-part video on finding multiple ways to solve the same problem and using all these different concepts that we've talked about: default dicts, min, sorted, and then a new data structure, priority queue. The next video is a conclusion video, and you'll go through everything that you learned in this course.